range of topics all the way from very smallest objects in the universe, like and to the biggest objects like the cosmology itself, the cosmos itself. So I hope that we have been able to convey the interesting features of such objects in a brief manner. And we have also conducted these talks in Kannada also with the view of encouraging our students and teachers to communicate more effectively, to overcome the barriers of language barriers. We have been doing that. So today's speaker is no exception. He knows Kannada very well. So you can interact with them after the lecture, after the talk. And he will speak for about 50 minutes, followed by question answer session. So before I request him to speak, I request our Joint Secretary, Professor Rudraswamy, to briefly introduce the speaker. Over to you, Professor Rudraswamy.
Thank you very much, sir, for this great opportunity extended. It is indeed a great honor and an immense pleasure for me to introduce a distinguished scientist and eminent speaker of today's online talk. Dr. Keshava Murthy got his PhD with Professor G. Ramachandran from Mysore University in theoretical physics. After a brief stint of teaching in Mysore University, he joined the service of IGCAR, Kalpakkam, Government of India as a scientific officer. Served as a head of radiation shielding and data division, head of Reactor Physics Division, and professor of Homi, Bhabha, National Institute, Mumbai. Guided many students towards PhD degrees, published many research papers in several international journals, delivered many invited talks sponsored by DAE at international forums, played key role in the preparation of design documents in prototype FBR and FBTR, contributed immensely to develop PADE approximation, which is being used worldwide, and developed a new kind of shield material to save cost substantially for use in fast reactor, which earned him a DAE award for this exceptional achievement. Post-retirements, he served as a visiting professor at Bangalore University and research professor at MS Ramaya University of Applied Sciences to carry out research under the sanctioned project in collaboration with BRC Mumbai. With this brief introduction, now I request Dr. R.S. Keshava Murthy, a distinguished scientist, to kindly deliver an important talk on nuclear power and AI. Over you to sir, and thank you very much.
Thank you, Dr. Rudraswamy, and I also thank KPA for giving me the opportunity. Anyway, I'm sorry for the delay. I somehow only restarting the computer solved the problem, even though I had given all the permissions. Anyway, this is something which is to be expected when you are dealing with, computer things. And this has happened often to several people earlier also. Okay.
Okay,
so,
please continue. Carry on. Please continue.
Okay. What I'm going to discuss today is the growth of AI and the power requirements for AI, why nuclear power is projected for AI, and lastly, AI in nuclear power. And I've used a lot of references, which I'm actually not quoting on the slides, but I have heavily dependent on the Lawrence Berkeley National Laboratory report in December 2024, and that is published for the United States Data Center Energy Usage Report. And also I have taken articles from MIT, McMaster University, recent IAEA, International Atomic Energy Reports, Goldman and Sachs report, McKinsey report, and of course, there are many others mentioned in the slides. I'm not going to mention them again, okay? So, the traditional AI focuses on performing a specific task intelligently. It has systems designed to respond to a particular set of inputs. These systems learn from data and make decisions or predictions based on that data. It makes predictions based on a predefined strategy. The traditional AI actually is not inventing new ways, but selects strategies it was programmed with. It makes smart decisions within a specified set of rules. Of course, you are already familiar with Alexa, or Google search algorithm. These have been trained to follow specific rules, do a particular job, and do it well, but they don't create anything new. Artificial intelligence has led to significant advances in technology. In fact, I would say that we were using, in a way, even though it was not called artificial intelligence, any computation is actually kind of making use of intelligent use of computation. In fact, when we started our job, as research scholars, as our work as research scholars, I used to get only 15 minutes of IBM 360 time in Bengaluru, in IISc. And that is nothing actually. Now, even an ordinary laptop is a billion times more powerful than these IBM 360, 370. There used to be kind of an excitement when we used to started using DEC 10, but DEC 10 is also nothing. When I joined IGCAR, it was Honeywell DPS 8 system, which had a huge area, but then they are nothing as compared to today's laptops. So, but it has led to actually significant advances, in technology and operational efficiencies. The next generation of artificial intelligence that can create something new. Of course, you already know all these things. Generative AI models are trained on a set of data and learn the underlying patterns to generate new data that mirrors the training set. So it can come out with something new. So traditional AI systems are primarily used to analyze data and make predictions, while generative AI goes a step further by creating new data similar to its training data. What about the knowledge requirements for generative AI? Generative AI systems need huge knowledge to create content. For example, GPT-3, ChatGPT was trained on about 45 terabytes of text data. This is equivalent of nearly a million feet of bookshelves, Traditional computer hardware is not enough at all to handle this data. It requires large clusters of graphic processing units. I'm sure you know about GPUs or tensor processing units. That's the latest, with specialized accelerated chips capable of processing all that data across billions of parameters in parallel. What are these foundation models? These are at the heart of generative AI. Large deep learning models pre-trained to create a particular type of content and can be adapted to support a wide range of tasks. A foundation model can be used for multiple purposes. Once the foundation model is developed, anyone can build an application on top of it to leverage its content. Okay. So it can, for example, it can create human quality text. Oh, the important thing is they're trained on massive data sets. This may include public data scraped from Wikipedia, government sites, social media, books, as well as private data from large databases. Developing foundation models requires deep expertise in each of the area. What about the cost? Training foundation models requires substantial computational resources required to support it. In the beginning of the training process, the model typically produces random results. To improve its next output, more in line with what is expected, it adjusts the weights of the underlying neural network. This is a very difficult problem, actually. So you may need millions of times to get to the desired level of accuracy. Currently, such training efforts can cost millions of dollars, take months. GPT-3 estimated cost was $4 million to $12 million. Therefore, the market is currently dominated by tech giants and startups backed by significant investment. In fact, now, private companies, Goldman Sachs or McKinsey, they are predicting something like $4 trillion economy coming out of this. So what are these data centers? We think that cloud computing is, it gives an impression that something is going on the clouds, somewhere in the internet, somewhere. Actually, all the hardware are housed in specialized facilities, housing vast networks of servers, storage, and networking gear, acting as the physical backbone for digital services. AI data centers, Amazon, for example, has got about 100 data centers around the world. They are huge. Data centers specifically optimizes infrastructure with powerful GPUs and high-speed interconnects to train and run complex AI models, requiring immense power and cooling. This is important. I'm coming to that. To manage huge data sets and computational demands, making them the factories of the AI era. Don't think that some things is there or sitting in the clouds. They are all physical and they are very power intensive. They contain powerful CPUs and specialized accelerators or tensor processing GPUs and TPUs, massive storage systems, and high bandwidth interconnects. NVIDIA link thousands of processors functioning as a giant supercomputer. What are important? Essential systems, air, liquid, to manage extreme heat generated by intensive AI processing. Is not that just our brain gets heated up. In fact, humans are far better. The computer chips get heated up, and 40% of the power is for cooling their brain. Robust, redundant power supplies, often from diverse sources, to ensure continuous operation is required. Renewables, clear, is one of the examples. I'm going to discuss that. They are optimized for high performance computing tasks. They use powerful GPUs and AI accelerators to train complex AI models, require much higher power density and more advanced cooling than traditional data centers. Massive warehouse-sized facilities. So, in other words, generative AI require more massive facilities than normal AI facilities. So what is the annual average server power draw? Kilowatt. You can see how it is going up these days. Okay. You can see how the curve is going up and up and up. It's about kilowatts range. And with 8 GPU, you can see how the power is going up. And this was the single processor case. They are all here below. The dual processor is here. The 8 processor is here on the left side. But this is AI non-accelerated, AI 2 GPU, AI 4 GPU, and then this is AI 8 GPU. So you can see there is a kind of an exponential growth in power requirements. So then these are the shipments. See, that is the power draw. And this is the server installed base. Nowadays, how many millions of servers are sold? 8 GPU AIs are sold of this order. More than 10 million, I think. The total number of millions is about 30 million. These are the total number of, so this multiplied by the power level will give you the power requirements. So it shouldn't be something like, I'm thinking of the analogy of the chess story. I think the chessboard story. The Raja asked for a boon. He said, you give the grain, the first one 2 grains, and the next one 4 grains, and the next 2 to the power of 3 grains. And the Raja felt it was so easy to do it. Yes, but it cannot be done at all. So you know that this kind of exponential growth can actually happen in the case of. So the power consumption, this is all US. Unfortunately, most of the studies are in US. The total data center electricity consumption is of the order of 600 terawatt hours. And the 6.7 to 12% increase in the total US electricity production. Imagine this actually corresponds to the total electricity produced in India.
Oh, very good.
Okay, so that is the future scenario range. So this is what is required for the power, and I'm sure it is going to go much higher. And what is the electricity consumption? Servers, okay, this again is another curve by server wise that is giving the same thing. Okay, so there is the order of 300 terawatt hour. Okay, so about 600 terawatt hour corresponds to about 150,000 megawatts. Okay, that is the total power requirement. And then what about the consumption? Data center itself, for its own infrastructure, it requires power. See, hyperscale, that has got its own power consumption. That's about 200 terawatt may be required. The projected thing is about 600 terawatt. The data centers themselves would require enormous power. Okay? And this is the most surprising thing to me. I did not know this. Bitcoin mining, okay, that requires something like 100 terawatt hour. What is this? I never expected Bitcoins to make an appearance in this scenario. That hash creation apparently is highly energy intensive. There's a string of hexadecimal numbers, that nobody can crack. That what is called the blockchain. That itself is taking so much power. So Bitcoin is not that way energy, is highly energy intensive activity. And some curious observations. This is appeared on the McMaster University study. One Google search uses about as much electricity as a home light for 17 seconds. Asking a generative AI model like ChatGPT, a single question is equivalent to that of light for 20 minutes. Having general AI generate an image can draw roughly the energy of keeping the light on for 87 consecutive days. So that is the thing. The hundreds of millions of people now using AI have effectively added equivalent of millions of new homes. Millions of new homes could have been, got the lighting. So the demand is only growing. The challenge for tech companies is that because tech companies are, interested in expanding, okay? So they want more and more sources of electricity that are well suited for AI. Okay, this is just for comparison. I have given what is going on in India. We have produced 1,700 terawatt hours in 2024-25. The demand is projected to surge to 4,000 terawatt hours. These are roughly equivalent of about 200 to 250,000 megawatt capacity. We have increased industrial activity, electrical vehicles. We too have data centers. In fact, NVIDIA has a big, presence in India. NVIDIA, incidentally, is the entire thing is in Taipei, Taiwan. Such a small country is so important. It is producing so much chips. Then 2024 production is up from 930 terawatt hour to 2,100 terawatt hour. Actually, even in India, you're seeing this growth. Renewable growths are not that high. Coal share actually is rising to 75%. Its share overall remains similar. So having, I projected India's thing only for comparison purposes. You know that the requirement for generative AI is of the order of the requirement for India. Okay. So what about the water consumption? When there is so much heat to be dissipated, our human brains, I think, are much cooler. Of course, we also say, nam tale bisi aitappa ant heltivi. It is literally true. Tale actually becomes busy. There is no doubt. Okay. So when a hyperscale thing requires water usage is high. Okay. It's about $50 billion. So at the higher end, it requires 300 billion lotus per year. For comparison, I have given whole of Karnataka domestic water consumption is only 1,100 billion. So 1/3 is used for AI cooling. Okay. And then for Bangalore alone, we are using something like 2 billion liters per year. Okay. So that is the kind of, these are all appearing in LBNL report. Okay. So then even this LBNL report compared to the current trends of the 2016, this is why I said the chessboard story. Even they were wrong. They were expecting only data center electric consumption to be of the order of 80 to 100. But now look at the way in which graph is going up. That is our problem. Okay. So you have to be circumspect, and this is actually ringing a warning bell. The pros and cons of power for AI. It requires vast amounts of computational power running around the clock. That is the issue. You want it to run around the clock throughout the world, often housed in energy-intensive data centers. Renewable energy sources like solar, wind provide intermittent energy. They don't guarantee the constant power supply these data centers require. These centers must be online 24/7, even when the sun is not shining and the wind is not blowing. And of course, fossil fuels have somehow, they have become some kind of anathema for Westerners, particularly because of the carbon footprint, these greenhouse gases. So, and also fuel prices can be unpredictable. The long-term availability of fossil fuels is also uncertain. So this is a problem for fossil fuels, even though actually our mainstay today in India is actually coal. So I never, people working in energy sector, we don't try to fault with each other. We would actually rather to think about, complementary and supplementary ways to provide energy to the general population. Naturally, this brings us to environmental concerns. Growth of AI needs enormous electric power. What are the important considerations? Waste, pollution, greenhouse gases, water. So we have to think why the tech giants are driven to a certain ways of thinking for providing power. Okay. Now, I think this is the way in which they have looked at it, I believe. What, of course, most important is the continuous availability. Okay. So coal is out for them because it is producing 970 tons for 1 gigawatt carbon dioxide. Huge, actually. And then it is giving deaths are also slightly more. And coal is giving 24.6 deaths. And then even oil is giving 720 tons of carbon dioxide. Natural gas is giving 450 tons. Biomass is giving about 78 to 230. Hydropower is less. Wind is less. Nuclear energy is less. Solar is less. Solar also has actually the whole, the consideration mostly has gone into nuclear and solar because both are low carbon and solar also is very cheap. And but the problem is not available 24/7. You can make it 24/7 by battery. You storage batteries, but storage battery requires materials, sometimes toxic materials. Actually, the waste produced per megawatt. So we always, the energy people, we always talk about per megawatt electricity. In the case of nuclear energy, it's about 20 kilos of waste, but of course, highly radioactive. In the case of solar, it's about 75 tons. In the case of nuclear, the total waste is about 20 kilos per megawatt. In the case of solar, it is 78. But this is all highly of the 20 kilos. Lot of radioactivity may be existing. It does exist. In the case of solar, about 150 kilos of toxic material is present. But I think for the big companies, what matters is only the availability. I think 24/7 availability for them, that has mattered a lot. And of course, these are the usual DI bhajan, how radiation when they talk about households. In fact, households give more radon sometimes. You know, my advice to you is never use fly ash bricks in your construction. Fly ash has a lot of radon. Okay. And then soil, cosmic. Well, these are the usual things, you know, to sell. Chernobyl 0.002, and then nuclear plants gives the minimum. These are all true. But anyway, these are United Nations Scientific Committee of the Effects of Radiation taken from that. And that is okay. This is one of the things. But even then, the acceptability of nuclear was not much earlier. But now it has picked up because of various other reasons. Solar also emits 40 times more radiation per unit energy than nuclear due to mining of rare earth metals. This is an important thing. It's not that solar you can construct out of nothing. No, you need materials, and that materials need to be mined. It has to be processed. So they require factories, they require water. So actually, when you are thinking of an option, you have to think of the whole life cycle of an option. Okay. So that way, actually, in my opinion, there is nothing to choose, because I always feel that conservation principle operates. You always get something at the expense of something else. Okay. So each thing has its own plus points and minus points. Okay. Then emissions. That way also solar, is slightly higher than nuclear. But this is not the main reason I'm telling you. The main reason is continuous availability for these people. Okay. So, okay, this is something important, I would say. Life cycle, steel, for example, tons per terawatt hour. Solar is also high as compared to nuclear. Nuclear is very low as compared to solar. Okay. Then what about the minerals? It requires car, lithium, nickel, manganese, cobalt, graphite, chromium, molybdenum. Okay. Nuclear, you can see it requires manganese, it requires copper. And so the mineral resources are important. How many kilos per megawatt is required? That's an important thing, actually. Electric cars require so much. You can see manganese, and many of them are very expensive and very difficult to mine. I don't know whether we have enough of these rare materials. Actually, rare materials is an important activity nowadays in each country. Okay. So this production, you can see why China is on the forefront, why people are afraid of China. Most of the rare earths, most of the important minerals are, the availability is very high only in China. Can you see that? Please stare at it. Yeah. Copper, nickel, cobalt, lithium, rare earths, everything that is needed for chips. This goes to show the kind of importance that China has on these matters, and therefore nobody can, play with China. And share of processing by volume. Look at China, copper, 40% of copper. Rest of the world is nothing. Lithium, look at lithium. We seem to have, we are always interested in lithium batteries. We are always talking of electric vehicles. And look at lithium production. We seem to have found some lithium in J&K, Jammu and Kashmir. I don't know, but it has not yet started anywhere. So our own, requirements, we are not able to meet from within India, or even rest of the world cannot meet. That's a problem. So this gets into a situation of demand and supply. Therefore, what is cheap today may not be cheap tomorrow. So this is another headache. As you see, whatever is true for fossil fuel can become true even for other, energy options. So rare earth is complete domination by China. The level of concentration is quite high in Chinese minerals. Okay. So solar panels also produce waste production. This I have already told you. It's not that they are free. And one more problem with solar for the big companies particularly is the land use. Solar requires about 50 times more land as compared to nuclear. You know that. So about 1,000 megawatt solar requires about 50 square miles or something. I don't know. I mean, that's an approximate figure. So all of the nuclear waste ever produced in the United States can fit in 50-foot stacks on a single football field. So that's how, but then the radioactive waste is a problematic situation. And of course, there are papers coming in to convince people that it can be handled. Okay. I don't think I'm going to touch upon that aspect in this car. Okay, in this talk. So naturally, considering the previously described considerations, the AI companies want nil grease emission, 24/7, lower water consumption, and much lower footprint. It should take less, because real estate is costly. They want, lower footprint. So generation 4 small modular reactors are considered. I mentioned here only 2 types. Of course, I am a reactor man. So if you want, I can talk about it at length. That is not my primary, topic today. One is the fast reactor. They can breed as well as they burn. They can go to very high burn-ups. Very high temperature reactors with the triso particle fuels can also go to high burn-ups. Of course, FBTR, I don't know how many of you have seen in Kalpakkam. I was there. I was also the reactor physicist for this. It's a 40 megawatt reactor, fast reactor. They are not moderated in case of fast reactors. So once you introduce water, it gets moderated. Therefore, the purpose of breeding gets lost because you want fast neutrons, fissions from fast neutrons. Some of them escape into fertile blankets, convert them into fuel. So that's the advantage of having neutrons fast. But the penalty comes in the way of enrichment. You need high fission rates because the thermal neutron fission reactions rates are about 500 times more than the fast neutrons. But then you can breed, that's one advantage. The other thing is you can go for high burn-ups. If you spend so much money on enriching the fuel and the fabrication, naturally you would like to go for high burn. And natural uranium reactors, you can go for a burn-up about 1 atom per cent burn-up, or approximately 10,000 megawatt days per ton. Whereas in the case of a fast reactor, you can go up to 100,000. In fact, in FBTR, we went up to 150,000 megawatt days per ton. The final limitation is coming from the clad failure. The steel cases, steel pins, steel tubes in which you stuff the fuel, that breaks. This is called clad failure. Okay, so because radiation damage is so high, it can do that. The average energy of neutrons in FBTR core is around 300 keV. The most advantageous thing is actually water consumption is less, and not only that, it breeds fuel. That's the advantage. And small reactors are inherently safe because they tend to escape out. All the safety analysis have shown absolutely safe. You don't really require any, big design towards mitigation of accidents. Okay, you need not plan for, supercriticality accidents. The other thing is the high energy, high temperature reactors. So this is using helium coolant, 1,000 degrees outlet temperature, 200 to 600 megawatt electric, solid graphite block core, okay, high thermal efficiency. One of the things that we want is high thermal efficiency, Carnot, higher the temperature, the difference between the temperature, operating temperature, and the temperature of the sink, you get higher efficiency, both fast reactors and in fact, the BRC is doing this now, the compact high temperature reactor. The advantage is you can use it for other purposes also, like hydrogen production and the water availability for other industries, like many of the metal industries. They can, in fact, they can be co-located. Some of these things, and that's the advantage. And also, one of the advantages is, um, graphite is highly radiation resistant, and the fuel for this is called triso fuel. So cylindrical compacts, of course, put hexagonal graphite blocks or prismatic reactors. That means hexagonal blocks, okay? And the fuel is surrounded by graphite, then surrounded by pyrolytic carbon, and then surrounded by silicon carbide. Silicon carbide actually is an extremely good material. It's highly radiation resistant, and Europeans never share any information with you on silicon carbide. We have tried to get some information. In fact, it can be used as clad material. It's very good. Actually, I wanted to plan some radiation damage experiments in Kalpakkam. I also got the electron spin resonance spectrometer for that, but then I retired. Okay. So these are very safe reactors, and they can be used for multi-purposes. And this is the reason why these are called generation 4 reactors, which are inherently safe, because silicon carbide, it's extremely good containment properties. It doesn't easily give up. Okay. And of course, there are other types of molten salt reactors and things like that. I'm not going into that. These are the only two that are enough for the day. Okay. So higher thermal efficiency, both are high temperature reactors. More energy can be extracted per ton of fuel. Lower radioactive. See, another thing is, if you go for high burn-up, in fact, most of the actinides also get burned. Therefore, because of that, you have lower radioactivity of actinides, which have large half-lives. Their ability to provide extreme clean process heat for industrial users. Inherent safety features, inert coolants like helium. Robust fuel that can survive extreme conditions. The thing is, of course, I have to tell you this, helium is not something easy to come by. Very expensive, of course, you should know. And then other things I already told you. Okay. What about artificial intelligence in nuclear reactors themselves? It's a very complex system consisting of multi-physics, multi-scale, and for different scales. Okay. So then there may be different parameters, assumptions, and models. In machine learning methods, especially supervised or semi-supervised learning, the quality of data has a significant impact on the results. Therefore, one of the challenges lies in the selection of a particular sampling method. In reactor physics, not just reactor physics, I will tell you, wherever you use extremely complex equations like Navier-Stokes, for example, it could be airplanes or complicated thermal hydraulics, any plant that involves complicated computational fluid dynamics, it involves a higher dimensional parameter space. In fact, in reactor physics, it's a 7-dimensional space, 3 for neutron, 3 for space, 1 for time. And traditional sampling methods become inefficient. In fact, that's the reason why we go for Monte Carlo. The acquisition of high resolution, high fidelity data is a big challenge. The generation of high fidelity data, statistical Monte Carlo, is highly computational resource intensive. Incidentally, I should mention something about Monte Carlo. Monte Carlo is not to be taken lightly. It's considered one of the great creations of the mankind. They have spent about 1,000 man-years to write the code. And it's not just the statistical aspects that are important. The way in which it can handle the geometries is extremely, efficient. And Monte Carlo official versions are not available to India as of now. And they, of course, consume enormous time, depending on your problem. If the attenuation is of the If the attenuations are high, they are highly computationally resource intensive. Because of this, foundational model creation is a bigger challenge. Physics-based generative AI is being pursued as a result. And but even then, these physics-based neural networks have a problem because of the the initialization conditions are not that easy. The convergence can become very slow, and it can give wrong results. Neural nets can give wrong results. The initial conditions, a problem. Uh, how many? It depends on the layers that you have, and then of course it also depends on the activation functions that you use. None of them are easy, unfortunately. So and then that's why they want to mix up the actual data from a reactor. So that is called, data. It is data enhanced physics informed neural network. It leverages external data sets such as simulated or sensor measured flux values. They add additional inputs. Of course, that is you would have heard about digital twin, maybe. So these are all actually as the reactors operate. I mean, it's not just the reactors, nuclear reactors. It can be anything. It can be aircraft, or it can be a plant for a very dangerous chemical, which are used in fertilizers, production. Anywhere, okay. Unfortunately, mankind is used to using very dangerous things, okay, very things which are not very good for human beings. So there, you require, this kind of digital twins that may be more safer. That's what people feel. So, but still, it's quite a complex situation. And the consistent convergence for physics-informed nuclear nets also is high-dimensional cases is very slow. So computational demands for training is very high, grows significantly. And then this data combined, mixing the actual data provides a promising avenue for enhancing the performance. People are at it. But I feel it will be okay when you start reading the literature on this kind of thing that is as complicated as doing the calculations by yourselves. Not only that, if you train a foundation, you have a foundational model, it becomes very reactor specific or a plant specific, then again you lose value. Okay, that is another problem, and that is so. Another question that I would like to ask is, can AI go wrong? Yes, plenty of examples from the literature. In fact, these are all light-hearted examples, exploiting a weakness in the system. Okay, a user instructed the chat box to agree to all requests. As a result, the bot agreed to sell a new Chevrolet car for $1 and make it a legally binding offer. In a New York federal court filing, one of the lawyers was caught citing non-existent legal cases. He had used ChatGPT to conduct legal research, and it provided fake case references. The National Eating Disorders Association, this is important, I feel, removed its chatbot because it gave dangerous suggestions related to eating disorders. The chatbot repeatedly recommended weight reduction, calorie tracking, the body fat measurements, practices that could worsen the condition in people struggling with eating disorders. Anyway, the foundational model itself does not have any experience, no. So, in fact, for me, I have been asking all the time, I have the habit of taking lemon and honey in the morning. And these lemon seeds used to be an annoyance. Instead of throwing, I started swallowing them. Then I just, out of curiosity, wanted to know what happens if I swallow these lemon seeds. Then, sure enough, I found Google telling me, what is that? This AI telling me it's good for health. Only chew it well. It is it's very good for your cardiac health. So now I am started chewing 2-3 lemon seeds, then drinking. But then I asked about orange seeds. It does not say it is good. It is good, it says, but then it may have cyanide, it says. I don't know. So you have to decide whether you have to give a value to this AI suggestions. And of course, it also given one very nice suggestion. Watermelon is annoying to throw the seeds out. So now I feel comfortable while chewing and taking along with the fruit. Okay. So, and then, okay, this, okay, and it's also generated, in fact, it advised in New York City, city's bureaucratic procedures, one-stop shop, it advised people to break the laws. Okay. It generated summer reading list that included non-existent books. Okay. So, in fact, in one of the things, apparently, urged users to eat rocks as a vital source of minerals and vitamins. Another error, this is a very funny error, mixing non-toxic glue into the sauce in response to queries about cheese slipping off the pizza. Most likely, this stem from misinterpreting jokes or content from, because it takes data from everywhere. In fact, on a serious note, I can tell you, I have glaucoma and I wanted to see, because my eye pressure recently went up. Actually, I'm undergoing a procedure tomorrow. I am repeatedly, I read about this. Does computer work increase your IOP, intraocular pressure? It says yes, it increases temporarily. If you do it continuously, it can lead to permanent, pressure rise. But then when I talk to doctor, every time I raise this doctor, I think doctor is fed up of people asking her every time. Every time she tells me, no, it does not have any impact. So I don't know why the AI says this. Okay, this brings us to general AI in decision making. It is being actively explored for use in the nuclear and aviation industries in supportive, non-autonomous rules, where human operators remain in command. Regulators and operators, I know I have faced safety committees. They require every calculation, everything be transparent and explainable, and to understand how they reach a conclusion, which is difficult with complex black box models. They require large amounts of high quality, unbiased data. A lack of data on rare extreme accident scenarios, nuclear or chemical plant or aircraft makes it difficult to train models for these specific situations. Increased reliance on connected AI systems expands the potential attack surface and cyber threats necessitating robust security measures is another problem. What about the environmental thing? Of course, we have already mentioned many, and this is an MIT study. A paper from MIT people, the Google and the University of California estimated the training process alone consumed 1287 megawatt hours of electricity, enough to power about 120 average US homes, generating about 552 tons of carbon dioxide. High power is needed to manufacture a GPU, okay? Intensive generative AI workloads. There are also environmental implications of obtaining the raw materials. This I have already explained to you, the mineral aspect of the industry can involve dirty mining procedures and the use of toxic chemicals, which I have already told you. And now look at the supply of GPUs. It was up from 2.67 million in 2022 to 3.85. Major players are NVIDIA, AMD, and Intel. Okay, what is the way forward? According to MIT professors, nothing is mine, this is just a, collection of, this kind of a literature survey that I have done, okay? Yeah. Except for a small part where I can say something on the nuclear side. The rest of the things are all collected from literature. According to MIT professors, the industry is on an unsustainable path, but there are ways to encourage responsible development. Generative AI that supports environmental objectives, a comprehensive consideration of all the environmental and societal costs, detailed assessment of the value in its perceived benefits. We need a more contextual way of systematically and comprehensively understanding the implications of new developments in this space. Due to the speed at which there have been improvements, we have had a chance to catch up with our abilities to measure and understand the trade-offs, okay? So to conclude, I'll say generative AI is spread is there everywhere, making an impact on almost all aspects of our life. But there should be judicious way or discrimination as to when and how to be applied, keeping the huge impact on environment. One of the things that I have in my mind is the impact on children itself. Nowadays all the toys are coming with chips, and I don't know what the child feels. I have no idea. In fact, all the games that they're quite used to, I don't know what they think of their own life. Is it just a life in a bubble? I have no idea. In fact, when I see my grandson playing with a ball, when the ball moves, it starts singing. I don't know whether the child thinks this is natural for a ball to sing. We know from our past experience and past literature survey, nowadays psychology is not something which anybody studies. This is a very bad thing. Actually, the importance of psychology is very high in our modern day lives. In fact, it appears the child learns physics and chemistry naturally. It knows when it is playing with waves, throwing, or water, flow, everything, it picks up instinctively. Most of the science, it picks up instinctively. But now that instincts are all ruined if you introduce, these artificial things on that. I don't know what is right and what is wrong. And then the children's toys are a huge market, these video games, they're all forming a huge, impact. So I would say, I don't know, I'll take this, our Kannada proverb, Gubbi Mel Brahmastra. I think one should not use Brahmastra on all gubbies, even small things, as it is not only disproportionate and unnecessary, but also results in additional collateral ecological damage. For example, it should not damage the psychology of our own children, I feel. I don't know whether it is correct or not. I feel strict scientific studies are required for that. Okay. So thank you all for listening.
Thank you very much, Dr. Keshava Murthy.
Yes.
Now it's time for some questions. If anybody ask any questions, they may raise their hands, and one by one we'll go through the questions. Be brief. Please be brief so that we can accommodate more number of questions.
Okay.
Rudraswamy, please ask your question. Rudraswamy. Okay, Rudraswamy, you may ask your question. Are you there, Rudraswamy?
Yes, sir. Thank you. Thank you, sir. Thank you for your nice presentation. You mentioned about the availability of many materials required for chips in China. Why these materials are not available in other countries? Is it due to other countries never tried tried exploration of these materials? And second question is, what is the difference between FBTR and prototype FBTR? And you also mentioned about 1,700 tetrawatt hour, generation in 24-25. What is the contribution from nuclear power? These are the three questions I have.
Okay.
Yeah.
Okay. The first question is, I think, leave it to you to think about. Because it depends on the country and the resources. Earth is not endowed with the same resources everywhere. And of course, it also requires efforts. The second one is prototype fast breeder reactor is different from, this is a test reactor. What we have, fast breeder test reactor. That is where we test the materials, any use of any material, anything in reactors requires extensive testing. So this provides a test bed. And it's not a power reactor mainly. It is for testing the materials at very high radiation and temperature. Okay. And the third one is the nuclear contribution in India is very little right now. It is about 7 to 8%. Not even that, I think. It's a very small percentage, and things are slow. That's all I can say.
Okay. Thank you, sir. Thank you very much.
Question. ನಾನೇನ್ ಕೇಳ್ಬೇಕಂತಿದೀನಿ ಅಂದ್ರೆ ಚೈನಾದಲ್ಲಿ ಮಾತ್ರ ಯಾಕೆ ರೇರ್ ಸಿಗ್ತಾ ಇದೆ? ಇದು ಜಿಯೋಲಾಜಿಕಲ್ ಪ್ರಾಬ್ಲಮ್, ಜಿಯೋಲಾಜಿಕಲ್ ಎಫೆಕ್ಟ್, ಅಥವಾ ಬೇರೆ ಕಂಟ್ರೀಸ್ ಅವರು ಎಕ್ಸ್ಪ್ಲೋರ್ ಮಾಡೋಕ್ ಆಗ್ತಾ ಇಲ್ವಾ? ವೈ ಓನ್ಲಿ ಇನ್ ಚೈನಾ ವಿ ಆರ್ ಗೆಟಿಂಗ್ ದಿಸ್ ರೇರ್ ಅರ್ತ್ ಎಲಿಮೆಂಟ್ಸ್ ಅಂತ ಮೆಟೀರಿಯಲ್ಸ್?
Actually, I do not know because the same question can be asked ಅಲ್ವಾ, ಯಾವ್ದಕ್ ಬೇಕಾದ್ರೂ ಕೇಳ್ಬೋದು. ಇವಾಗ ಆಯಿಲ್ ಯಾತಕ್ಕೆ ಜಾಸ್ತಿ ಇದೆ ಮಿಡ್ ಈಸ್ಟ್ ಅಲ್ಲಿ, ನಮ್ ದೇಶದಲ್ಲಿ ಕಮ್ಮಿ ಇದೆ. ಆಮೇಲೆ ಆಸ್ಟ್ರೇಲಿಯಾದಲ್ಲಿ ಯಾತಕ್ಕೆ ವೆರಿ ಗುಡ್ ಕ್ವಾಲಿಟಿ ಓರ್ ಇದೆ, ಯುರೇನಿಯಂ ಓರ್ ಆಸ್ಟ್ರೇಲಿಯಾದಲ್ಲಿ ಇದೆ, ನಮ್ಮ ಹತ್ರ ಇಲ್ಲ. ಈ US ನವ್ರಿಗೆ ಜಂಬ ಏನು ಅಂದ್ರೆ ಎಲ್ಲಾ ಇದೆ ಅವ್ರ ಹತ್ರ ಅಂತ. ಬಟ್ ಇವಾಗ ಸ್ವಲ್ಪ ಚೈನಾ ಅವ್ರಿಗೆ ಬಹಳ ಇದ್ ಮಾಡ್ತಾ ಇದೆ. ಸೊ ಕೆಲವು ಕಂಟ್ರೀಸ್ ಅಲ್ಲಿ, ಕೆಲವು ಈಗ ಚಿಲಿನಲ್ಲಿ ಕಾಪರ್ ಇದೆ ತುಂಬಾ. ಇದು ಮದರ್ ಅರ್ತ್ ಯಾಕೆ ಹೀಗೆ ಮಾಡಿದೆ ಅನ್ನೋದು ಅದು ಜಿಯಾಲಜಿಸ್ಟ್ಗಳನ್ನೇ ಕೇಳ್ಬೇಕೇನೋ ಪ್ರಾಬಬ್ಲಿ.
ಅದೇ any other questions? Dr. Kulkarni wanted to ask. Dr. Kulkarni.
Okay.
ಇಲ್ಲ, ಅವರೆಲ್ಲ ಹೋಗಿದ್ದಾರೆ. Dr. Srikanth, please ask your question.
Yes, sir. Sir, good morning, sir. Good morning.
ಕೇಳಿ, continue.
Okay. Sir, as of now, to what extent AI used in nuclear reactors?
I would say very little, because nuclear reactors cannot be operated, they have to be operated on a standalone mode, and much of the electronics and security systems have to be standalone because it is prone to security risks. In fact, in Kalpakkam or in BRC anywhere, I know, to my knowledge that I have, we never use, we call the electronics that is available outside, like laptops and all that are roadside electronics, we call it. And the security, reactor grade computing systems are very expensive. They should never fail. So whatever software you use there one should never be able to hack. Okay. So it cannot be connected with the outside world. That's the reason.
Okay. Innondu, you mentioned about simple questions. We have heard about CPU and GPU.
Yes.
TPU, tensor processing units, andre ಏನು? Can you give us some idea about how are they different from GPU?
Okay, I'm not very knowledgeable about tensor processing units. To the extent that I know, it is something like, the scales in which is scale of processing. That is where the differences come actually. So this is all application specific integrated circuits. This is actually kind of an accelerator. Okay, that's a kind of an accelerator chip.
Even though you mentioned these rare earth elements are required in the manufacture of chips, what are required? Because I'm not a very solid state person. Why these elements or materials are required in the manufacturing of chips? How do they play the role? I thought only silicon or chips ಸಾಕಾಗುತ್ತೆ ಅನ್ಕೊಂಡಿದ್ದೆ. Why especially required in the manufacturing of the specialized chips and rare earth materials? How are they useful?
I really don't know how exactly they use. I have no idea. What is the? I mean, you are asking about the
rare earth materials.
What is the? I mean, at the chip level, what are the materials that are used? That fabrication process, I don't have any details as of now.
ಇನ್ನೊಂದು ನೀವು ಸರಿಯಾಗಿ ಹೇಳ್ತಾ ಇದ್ರಿ, AI is now being misused ಅಂತ, ಬಹಳ ಮಿಸ್ಯೂಸ್ ಆಗ್ತಾ ಇದೆ. ಪ್ಲಾಸ್ಟಿಕ್ ತರಾನೇ ಕೂಡ AI ನಾವು ರಿಸ್ಟ್ರಿಕ್ಷನ್ ಹಾಕ್ಬೇಕು ಅಂತ ಅನ್ಸುತ್ತೆ. We have to put a restriction condition.
ಹೌದು, ಇವಾಗ ನೋಡಿ, ಅದು ಜನರೇಟಿಂಗ್ ಎ ಡಯಾಗ್ರಾಮ್ is okay for fun for some time, but if it is done repeatedly by large number of people, then it has an impact. See, that's the problem. And a human mind can do it very easily without much expense, isn't it?
Yeah, it is becoming a big plastic menace ತರ, ಅದು menace ಆಗ್ತಾ ಇದೆ ಒಂಥರ ಅಂತ ಅನ್ಸುತ್ತೆ.
It is becoming menace. Actually, ultimately the power requirement may grow like that chess story only, I feel.
Sir, ನಂದೊಂದು ಕ್ವಶನ್ ಇತ್ತು. KM Raghavendran here.
ಹೇಳಿ.
ತಾವು ತುಂಬಾ ಕರೆಕ್ಟ್ ಆಗಿ ಹೇಳಿದ್ರಿ. ದಿ ಅಮೌಂಟ್ ಆಫ್ ಪವರ್ ದಟ್ ಇಸ್ ಬೀಂಗ್ ಕನ್ಸ್ಯೂಮ್ಡ್ ಇಸ್ ಆಕ್ಚುಲಿ ಫ್ರೈಟ್ನಿಂಗ್. ಒಂದು ಕಡೆ ಸಸ್ಟೈನಬಲ್ ಗೋಲು, ಈ ಗ್ರೀನ್ ಎನರ್ಜಿ ಬಗ್ಗೆ ತುಂಬಾ ಹೇಳ್ತಿದ್ದಾರೆ. ಹಲವಾರು ಕಂಪನಿನೂ ಅದರಲ್ಲಿ ಇನ್ವೆಸ್ಟ್ ಮಾಡ್ತಿದ್ದಾರೆ. Now,
Okay.
is there some effort by these big companies to kind of create data centers which are
Yeah.
powered by renewable energy sources? Solar farms agirbodu ಅಥವಾ window ಆ ಥರ, ಅಥವಾ is that power not enough?
ನಾನು ನಿಮ್ಗೆ ಹೇಳಿದ್ನಲ್ಲ ಅದನ್ನೇ, ನಿಮ್ಗೆ
ಹೆಂಗೆ?
ಅದನ್ನೇ ಹೇಳಿದ್ ಇವಾಗ. ಮೈ ಪ್ರೆಸೆಂಟೇಶನ್ ವಾಸ್ ವೈ big tech giants are going towards nuclear anta. Nuclear also is considered green. You
Green.
know that because it is green in the sense it doesn't produce any of these greenhouse gases. Actually, I was working in a on environmental aspects of fast reactors also. Zero emission. Actually, we don't emit anything. Even radioactivity emission is nothing. The main problem in reactors business is only the radioactive waste. That's all. Even accidents are now few and far between, and they are much less. Okay, that's a different talk altogether. Material for another talk. So why they are driven towards this? Andre, one though it's green, okay, and
Okay.
the emissions are very low. The other thing is they have lower footprint. They require very small space. Okay, that is another thing. And they want all the AI centers want 24/7 power. They always want high power, continuously running.
Thank you, sir. Thank you.
Right.
Clear.
Any other questions? Professor Nagaraj, would you like to ask any questions?
Kulkarni, he raised his hand. Sir, Professor Kulkarni.
ಎಲ್ಲಿ ಅವ್ರು ಬರ್ಲಿಲ್ಲ, ಎಲ್ಲ ಹೋದರ್ ಕಾಣುತ್ತೆ. He is not available.
Sir, ನಂದೊಂದು ಕ್ವಶನ್ ಇಲ್ಲಿ.
ಕೇಳಿ.
Very high temperature reactor outlet temperature is about 1000 degrees Celsius ಅಂತ.
Outlet ಅಲ್ಲ ಅದು. Outlet. ಹೌದು.
Outlet temperature.
Correct.
What may be the temperature inside the core ಅಂತ ಅನ್ನೋದೇನಾದ್ರು?
No, inside core ಏನೇ ಅದು. See, inlet ಅಂತಂದ್ರೆ when the coolant starts going into the reactor, then it is low. Okay. It can be helium antandre, it can be even room temperature, But in the case of sodium, it has to be high. It will be 380 degrees in the case of sodium. When it comes out, it picks up heat on the way. Fissions produce heat, fissions produce energy. That energy is deposited in the fuel matrix and that produces heat. Okay. So that heat is removed. After all, ಇವಾಗ ನೀವು ತುಂಬಾ ಹಾಟ್ ಆಗಿರೋ ಹಾಲನ್ನ ಬೇಗ ಕಾಯಿಸ್ಬೇಕು ಅಂದ್ರೆ ಏನ್ ಮಾಡ್ತೀರಾ? ಇನ್ನೊಂದು ಪಾತ್ರೆ ಒಳಗೆ ನೀರ್ ಇಟ್ಬಿಟ್ಟು ಅದ್ರ ಒಳಗಡೆ ಇಡ್ತೀರಾ? ನೀರು ಹೀಟಪ್ ಆಗ್ತವಾ? ಅದೇ ತರನೇ ಅಷ್ಟೇ. ಅದಕ್ಕೆ ಹೀಟ್ ಎಕ್ಸ್ಚೇಂಜರ್ಸ್ ಅಂತ ಕರಿತೀವಿ.
ಐ ಥಿಂಕ್ ಯಾರ್ದು ಕ್ವಶನ್ಸ್ ಇಲ್ಲ ಅಂದ್ರೆ ಸರ್ ಸಾಕಷ್ಟು ಕವರ್ ಮಾಡಿದಿರ, ಎಸ್ಪೆಷಲಿ ದಿ ಪವರ್ ಕನ್ಸಂಪ್ಷನ್ ಅಂಡ್ ದಿ ವಾಟರ್ ಕನ್ಸಂಪ್ಷನ್ ಇನ್ ಕರ್ನಾಟಕ, ಇನ್ ಇಂಡಿಯಾ and even other parts of India. In fact, especially power consumption in Karnataka ಹೇಳಿದ್ರಿ 1100 liters billion liters ಅಂತ. ಸೊ ಇವೆಲ್ಲ ಡೇಟಾನ ಹೇಗೆ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ್ದಾರೆ ಅಂತ ಏನಾದ್ರು ಒಂದು ಐಡಿಯಾ ಇದೆಯಾ?
ಅದೆಲ್ಲ ಅವ್ರಿಗೆ ಆಕ್ಚುಲಿ KRS ಅಲ್ಲಿ ಎಷ್ಟಿದೆ ನೀರು ಅಂತ ಗೊತ್ತಿದೆಯಲ್ಲ. ಸಿವಿಲ್ ಇಂಜಿನಿಯರ್ಸ್ ಎಲ್ಲ ಗೊತ್ತಿರುತ್ತೆ ಏನ್ ಮಾಡ್ಬೇಕು ಅಂತ. ಇವಾಗ ನಿಮ್ಗೆ ಬೆಂಗಳೂರಿನಲ್ಲಿ ಎಷ್ಟು ಸಪ್ಲೈ ಇದೆ ಅಂತ ಗೊತ್ತಿರೋದಿಲ್ವಾ? ಪಂಪ್ಸ್ ಅಲ್ಲಿ ಎಲ್ಲ ಮೆಷರ್ಮೆಂಟ್. ಇವಾಗ ನಿಮ್ ವಾಟರ್ ಮೀಟರ್ಸ್ ಇದೆ ನಿಮಗೆ. ಹಳ್ಳಿಯವ್ರಿಗೆ ಬೇರೆ ತರ, ಅವ್ರದ್ದು ಡ್ಯಾಮ್ಸ್ ಇಂದ ಬಿಡ್ತಾರೆ, ಆಮೇಲೆ ಕೆರೆಗಳಿಂದ ಗೊತ್ತಾಗುತ್ತೆ. ಡೊಮೆಸ್ಟಿಕ್ ಯೂಸ್ ಎಷ್ಟು ಬರುತ್ತೆ ಅಂತ ಅದನ್ನ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತಾರೆ. ಅಗ್ರಿಕಲ್ಚರಲ್ ಯೂಸ್ ಇಸ್ ಡಿಫರೆಂಟ್. ದಟ್ ಇಸ್ ಹ್ಯೂಜ್ ಆಕ್ಚುಲಿ. ಓಕೆ,
ಎನಿವೇ ಸರ್, ಸಾಕಷ್ಟು ಕವರ್ ಮಾಡಿದೀರಾ. ನೀವು ಜಾಸ್ತಿ ಫಾಸ್ಟ್ ಬ್ರೀಡರ್ ರಿಯಾಕ್ಟರ್ ನೀವು ವರ್ಕ್ ಮಾಡಿದ್ದು ಹೇಳ್ತೀರೇನೋ ಅನ್ಕೊಂಡಿದ್ದೆ, ಆದ್ರೆ ನೀವು ಅದ್ರ ಬಗ್ಗೆ ಜಾಸ್ತಿ ಹೇಳಲಿಲ್ಲ. ಎನಿವೆ ಇನ್ನೊಂದು ಟಾಕ್ ಅಲ್ಲಿ ನೀವು ಅದನ್ನ ಮಾತಾಡಿ ಅಂತ ಕೇಳ್ಕೊಳ್ತೀವಿ. ಅಂಡ್ ಇನ್ಫ್ಯಾಕ್ಟ್ ಟು ಅವರ್ ಆಡಿಯನ್ಸ್, ನಾವು ವಿಜಯ ಕಾಲೇಜಿನ ಒಂದು ಗ್ರೂಪ್ ಸುಮಾರು 15 ಜನ ಕಲ್ಪಾಕಂ IGCARಗೆ ಹೋಗಿದ್ವಿ. ಇವರು ರಿಟೈರ್ ಆಗಕ್ಕೂ ಮುಂಚೆ ನಮ್ಗೆ ಅಲ್ಲಿ ಎಲ್ಲ ತೋರಿಸಿದ್ರು. ಒಂದೇನ್ ನನಗೆ ಇವತ್ತಿಗೂ ಕೂಡ ನೆನಪಿರೋದು ಅಂದ್ರೆ, ಒಂದು ಇನ್ಸ್ಟ್ರೂಮೆಂಟ್ ಪೆನ್ ಟೈಪ್ ಕೊಟ್ರು. ಯು ಕೀಪ್ ಔಟ್ ಸೈಡ್ ಅಂಡ್ ದೆನ್ ಯು ಸ್ಟ್ಯಾಂಡ್ ಆನ್ ದಿ ರಿಯಾಕ್ಟರ್ ಅಂಡ್ ನೋ ಡಿಫರೆನ್ಸ್ ಇನ್ what is that called, emission of radiation on the above the reactor and even outside. And that was I think I wanted an explanation for that. Anyway, he has covered a lot of things with respect to the power reactors. So thank you very much, sir.
Okay.
And in
ಅದು
fact, you have
ವೇಸ್ಟ್
extended
ಈಗ ಮೇಜರ್ ಇಶ್ಯೂ.
our-
ಈ ವೇಸ್ಟ್ ನ ಇವಾಗ ನ್ಯೂಕ್ಲಿಯರ್ ವೇಸ್ಟ್ ಅಂದ್ರೆ ಇಟ್ ಇಸ್ ನಾಟ್ ಅನ್ ಆರ್ಡಿನರಿ ವೇಸ್ಟ್. ಆಕ್ಚುಲಿ ಇಟ್ ಹ್ಯಾಸ್ ಲಾಟ್ ಆಫ್ ಎನರ್ಜಿ ಇನ್ ಇಟ್. Some people are trying to make use of the. In fact, ಈಗ ನ್ಯೂಕ್ಲಿಯರ್ ಡಯಾಗ್ನೋಸ್ಟಿಕ್ಸ್ ಅನ್ನೋದು ಎಷ್ಟರ ಮಟ್ಟಿಗೆ ಉಪಯೋಗಿಸ್ತಾರೆ ಅಂದ್ರೆ ಐಸೋಟೋಪ್ ಯೂಸ್ ಇಲ್ದೇನೆ ಡಯಾಗ್ನೋಸ್ಟಿಕ್ಸೇ ಇಲ್ಲ ಇವಾಗ ಆಸ್ಪತ್ರೆಗಳಲ್ಲಿ. ಅದರಿಂದ ಅದನ್ನ ದೇರ್ ಆರ್ ವೇರಿಯಸ್ ವೇಸ್ ಆಫ್ ಕನ್ವರ್ಟಿಂಗ್ ದಟ್ ಇನ್ ಟು ಎನರ್ಜಿ, ಸ್ಮಾಲ್ ಎನರ್ಜಿ ಸೋರ್ಸಸ್ ಮಾಡಬೇಕು ಅಂತಾನು ಇದೆ. ಐಸೋಟೋಪ್ ಪ್ರೊಡಕ್ಷನ್ ಬೇಕೇ ಬೇಕಾಗುತ್ತೆ. ಇನ್ನೊಂದು ಮೆನಿ ಆಫ್ ದಿಸ್ ವೇಸ್ಟ್ ದೇ ವಾಂಟ್ ಟು ಮೇಕ್ ಯೂಸ್ ಆಫ್ ಫಾರ್ power sources for space missions also. So I don't know, but these are all a slow going process, and I don't know. This again, I thought nuclear power has gone because it became very unpopular, particularly in Germany. In France, of course, it is still 70% of the electricity is nuclear, but in US it came down, but now it is picking up again. I don't know. So these are all cycles, for any proven concept. It shows that any proven concept will not go away. It is going to stay, but it is up to you to make use of it in a judicious way. I'm not saying that everything should be nuclear. I'm not saying everything should be solar. We should, use our discrimination and judgment as a society. So we should know what is good for our society and then do it accordingly.
Okay.
So,
Thanks, sir.
anyway, to our audience, Professor Keshava Murthy is also the life member of our association, Karnataka Physics Association. We should thank him because he has given his time and explained about the power reactors and AI. So thank you very much, sir. And from Karnataka Physics Association, we thank the guest. I think other invited members have also, I think, heard his talk, and we should thank, and we have to thank our own members. In addition to that, we should thank Dr. M.K. Raghavendra, who is supplying the Zoom platform, and S. Venkatraman and Professor B.A. Cogley for arranging all these things. So thank you one and all. I think in all probability next week, December 14th, we are going to have a talk from Pushpalata Bhatt from America about around 9:30 a.m. She has accepted to give a talk on December 14th. Okay. This is what the information for our members. Thank you very much. And I don't know whether Professor Cogley has got something to say about any other things.
Requesting all the members to join again next week, and also week after that we have fixed up a speaker also. 21st also we have fixed a speaker. So please join and participate in these meetings. And very informal type of meetings, so nothing to worry too much about. So with these few words, I am now requesting all of you. I'm ending the meeting. So we'll all meet again next week at the same time. We'll give you the link by Monday or Tuesday. We'll send you the link for joining the meeting. Thank you very much. Okay.
Thank you, sir.
Thank you very much.